will discuss the central equation of linear algebra, Ax is equals to b. So first, let us understand the meaning of Ax is equals to b. What does this equation mean? So in linear algebra, Ax is equals to b, if we talk about, it is not just a formula, it is a mathematical sentence. So depending on your goal, it can be read in two ways. It can be a system of constraints or a geometric movement. So in this equation, ax is equals to b. This A is the relationship matrix, or you can call it the rule. A is the rule. We'll discuss it in detail, what the rule means. X is the input, the knobs, and B is the result, the goal. Now, all these components we will discuss in some good detail. So first, let us understand what do we mean by matrix A, which is representing the rule, the word. So matrix A, it defines the environment or the physics of the problem. So matrix A, it is representing the data, the transformation, and also the relationships. So if matrix A is representing data, then you can treat it as your library of information, like database of user movie ratings. So this matrix A, it can store data. It can even store transformations. If it is storing transformations, then it is acting as a machine that takes an input and moves, rotates, or stretches into a new position. Because if this matrix A, it is storing the transformations, then it will decide how to transform an input. And in this equation, X is the input. So this A, the values of the A, it will decide how to transform inputs present in the X, how to rotate, how to move, how to stretch it into a new position. Now the matrix A, it can also store relationships. So if it is storing relationships, then it is mapping how the inputs interact. So in a neural network, this relationship, we call it like the weight matrix, that determines how much importance to give to each piece of incoming information. So weight matrix is like how much importance to give to the inputs. So now it's very clear to us that if we talk about the matrix A, it defines the environment, the rule, the word. Now this matrix A, we can store either the data in it, either the transformations or the relationships. If we are storing it data in A, then it will act like a database of information or library of information. If we are storing transformations in matrix A, then it will act like a machine wherein it will decide how to transform inputs, because we multiply the input present in the X with A, and this A can also store relationships. Then we will call this A as relationship matrix. And in neural network, we call it the weight matrix, wherein this A holds the weight, which determines how much importance to give to each piece of incoming information. Now let us look at the vector X, the input, the knobs, what it is. So the vector X, it represents the specific configuration or the ingredients you are feeding into the system. So vector X is basically the specific configuration or the ingredients you are feeding into the system. So vector X, it can represent either the unknowns, the parameters, the features, the weights. If it is representing unknowns, like if the vector X is representing unknowns, so in classical algebra, X is what you are trying to find. Like how much of ingredient A and ingredient B do I need? So now it's very clear to us that if I talk about this X, it can represent an unknown which we are trying to find. Like how much of A should I use to get B, small b. This vector x, it can also represent parameters or the weights. So in machine learning, x represents the features of the data, like the height, weight, and age of a patient. So this vector x, it can represent features, it can represent weights or parameters. Like for a patient, it can be the height, weight, and age of a patient. This vector x, it can also represent the knobs. So you can think of x as a set of sliders. By changing the values in x, you change how much of each rule in matrix A is applied. So this is very interesting. So if A is containing some information or some rules or some transformations, then this x can act like a knob. Like let us suppose A is containing information, library of information. This A will act like a knob, like a filter. So by changing the values in this x, so vector x is acting like a knob, filter. By changing the values in x, you can change how much of each rule in matrix A is applied. So this is the importance of vector x. So now it's very clear that if I talk about vector x can represent specific configuration. It can act like a knob, or it can represent the unknowns, the ingredients you are feeding into the system. So we can represent unknowns. So x, vector x can represent unknowns. It can represent the features, the parameters, the weights, or it can represent the knobs. Now we can look at the vector b. So vector b is the result, the goal. So in simple terms, vector b is the outcome of the interaction between a and x. So when a and x will interact, the outcome is what the vector b is. So vector b, it can represent, like it represents the output of the interaction of a and x. It represents the target, the observations. So if the vector b is representing the output, then it is basically the final destination after the transformation. Like if A is a rotate 90-degree matrix and X is your starting point, B is where you land. So vector B can represent output, and if vector B is representing an output, it is representing the result of interaction between A and X. Similarly, vector B, it can represent target or observations. So in artificial intelligence, vector B is often the ground truth, the actual label. So in artificial intelligence, especially in supervised learning, we already have the target variable. Like for this input, this should be the output. So the known output, the known labels is what the vector B represents. So in AI, vector B can also be represented as targets or observations. So whatever the known labels we know, that is what the vector B is, the actual label, the ground truth. And vector B can also be the solution. So vector B can also represent the solution. So the idea is that we often know the matrix A, our data, and vector B, our desired outcome. And we use linear algebra to work backward to find the perfect X that makes the equation true. So this vector B can be the solution. So we know the solution, we know the matrix A, and using linear algebra, we will calculate the X, because we know that vector X can be an unknown. It can represent unknown. So now it's very clear to us that if I talk about vector B, that vector B can be an output, like vector B can represent output. So output means it's the outcome of the interaction between A and X. When A and X will interact, the result is what the vector B is representing. The vector B can represent target or observations. The ground truth in artificial intelligence, the ground truth, the actual label is what can be represented as vector B, and vector B can also represent the solution. So using this and the matrix A, we can find the unknown vector X. If we put it all together, the three perspectives, so if the perspective is solving, then X is unknown. So if the perspective is solving, then what exactly we are doing is, given the matrix A, what what input X should be given to get the result B. So that is what solving means. Solving means solving for the unknown X. That can be one perspective. The other perspective of using this equation can be transforming. So in transforming, what we do is that B is unknown. In transforming, B is unknown. So the idea is very clear that, okay, we apply some set of transformations. The rules is represented by the matrix A. So if I apply these rules, which is given by the matrix A, to this input X, where do I end up? So that is what transformation is. So we can make use of this equation for transforming, for solving, and for learning. So in learning, A is unknown. So in learning, what we are asking is, given these inputs X and these results P, the ground truth, what are the underlying rules A? So in learning, we are trying to find the relationship matrix. Like if this is the input, this is the output, how input and output are related to each other. So the matrix A will be treated as a relationship matrix. Matrix A will represent the relationship matrix or the weight matrix. So now it's very clear to us that the equation Ax is equals to B. Now it's very clear in linear algebra, Ax is equals to B is the central equation. We can use this equation from the perspective of solving, where X is unknown, from the perspective of transforming, where B is unknown, and from the perspective of learning, where A is unknown. Now let us look at the geometric interpretation of the equation Ax is equals to B. The geometric interpretation. So let us look at Ax is equals to B as transformation. So in the geometric view, we stop thinking about solving equations and start thinking about moving through space. So we stop solving equations and start thinking about moving through spaces. So the idea is that, let us suppose we are starting with some original space. We are applying some transformation, and because of that, we will get a new space, a transformed space. So that is what Ax is equals to B as transformation is. So A contains the transformation rules, X is the input. So if we apply the transformation rules on the input, we get a transformed space, and that is what the B is. So here X is the input, A is the transformation rule, and B is the output, the transformed space we got. So the vector X, which is the input, it starts at one location, and the matrix A, which contains the rules, transformation rules, it acts as a force that moves the vector X into a new location, vector B. So vector matrix A is acting like a force which will transform the input vector X into a new vector B, into a new space. So here matrix A is the space wrap. So matrix A acts on X to move it to B. Now we will discuss the concept of linearity and basis in this transformation. So if I talk about linearity, the idea is that uh, after applying the transformation also, the concept of linearity states that the origin always stays fixed and all parallel lines remain parallel after the movement. So that is what linearity is. So linear transformation. So linear transformations are those where origin will not get shifted and all the parallel lines after transformation they will stay parallel. So that is the linearity in transformations. And what is basis? So matrix A essentially tells the computer where the standard directions like up and right should land in the new space. So bases are like the standard directions which helps in transforming the input X into a new space B. And matrix A, it contains the transformation rules. Matrix A contains the rules which tell where the standard direction should land in the new space. And these standard directions are the basis. Now we will look at the four key moments. The four key moments, like the four major transformations that we can do. The first one is the rotation. So the matrix spins the vector around the origin without changing its length. So in rotation transformation, we don't change the length, rather we just spin it through some angle. So the matrix A, it spins the input vector without changing its length. So in artificial intelligence, rotation is used in computer vision to recognize objects regardless of their orientation. So the idea is that if we have a cat which is tilted 45 degrees, then uh, computer vision makes use of a rotation matrix to rotate it to the normal angle and then process it. So that's the application of rotation transformation in computer vision. Like let us suppose I have a cat which is rotated 45 degree. So we will make use of this rotation transformation to bring it back to the normal angle and process it further. So in rotation, we the transformation matrix, it just spins the input vector without changing the length. Then the next transformation is the scaling. The next transformation is the scaling. So in scaling, the transformation matrix, it stretches or shrinks the input vector along certain axes. So scaling means either stretching or shrinking the input vector along certain axes. So that's the idea of scaling. So the transformation matrix A, it stretches or shrinks the input vector along certain axes. So in data, this scaling is normalization. If one feature has huge numbers and another has small numbers, like salary can be big, age can be 2-digit number, salary can be 5-digit, 6-digit, 7-digit. So we use a scaling matrix to put them onto the same playing field so the AI does not get biased towards the large numbers. So that technique is the normalization. And normalization makes use of scaling. Then the next transformation which we have is the projection. So projection is like casting a shadow. Projection is like casting a shadow. So it takes a high dimensional vector and flattens it onto a low dimensional surface, like from 3D to 2D. That is what projection is. So in projection, the transformation matrix, it takes a high dimensional input vector and transforms it into a low dimensional space, like from 3D to 2D space. That is what projection is. In graphics, this is how a 3D video game world is displayed on your flat 2D monitor. And in data science, it is how we take 1000 different data points about a person and project them onto a single risk score. So that is what projection transformation is. Then the next transformation is the compression. That is a shearing and squashing. So here the transformation matrix, it collapses the space. So compression means collapsing the space. So if the matrix is singular, Singular matrix means determinant is 0. If the determinant of the matrix is 0, then it's a singular matrix. Then it squashes the entire space into a flat line or a single point. So in compression, the transformation matrix, it will compress the space of the input vector. It will squash the input vector either into a flat line or a single point. In artificial intelligence, this is the core of autoencoders. So we take a high definition image and squash it into a tiny vector that captures only the most essential information, and then we try to reconstruct it later. So squashing is what compression is. So now it's very clear that four transformations we can perform: the rotation, the scaling, the projection, the compression. Each has got its own significance. They have a role to play in AI as well. Now let us look at why this matters for AI. See, when a deep learning model thinks, it is actually passing your input through a sequence of these transformations. So deep learning is basically a sequence of transformations. So in layer 1, the deep learning in the layer 1, it might be rotating the input vector to find edges. In layer 2, it might be scaling the input vectors to find shapes. So in layer 2, it might be scaling the edges to find shapes. And in layer 3, it might be projecting the shapes into a category like a face, a background. And linear algebra is the study of these geometric actions in the AI's brain. So now it's very clear that geometric transformations do have a role in AI. So linear algebra is the study of these geometric actions. By understanding the transformation matrix, we know exactly how the data is being reshaped as it moves through the brain of the AI. Now we will discuss why this matters for machine learning, like why the central equation of linear algebra AX is equals to B matters for machine learning, or what is the significance of the equation AX is equals to B in machine learning. So machine learning is mostly matrix operations. In machine learning, we will be coming across lots of matrix operations. So at its core, machine learning is finding a mathematical function that maps inputs to outputs. So in machine learning, we know the input, we know the output, but we don't know the mathematical function. So machine learning at its core is the process of finding a mathematical function that maps inputs to outputs. So we know inputs in machine learning, we know the outputs, and we determine the unknown function. Because we deal with thousands of inputs simultaneously, linear algebra is the only way to perform this mapping efficiently. So now let us see how most famous ML algorithms are actually just specific matrix operations. So if we talk about linear regression, so linear regression is basically AX is approximately equal to B. So in linear regression, we are predicting a continuous value like a house price based on the input features. So we are predicting a continuous value based on the input features. So in linear regression, this central equation of linear algebra AX is equals to B, if we consider, so the matrix A, so here is the representing the historical data. So in linear regression, this matrix A is the historical data matrix. Vector B is the actual prices, the ground reality, the ground truth. And vector X is the weight or importance of each feature. So in linear regression, A is the historical data matrix, vector B is the actual price vector, the ground reality, and vector X is the weights vector. So in the real world, a perfect solution usually does not exist because the data is noisy. So in linear regression, we are searching for x. So we are solving this equation to find the unknown x, because b we know, capital A we know, x we are solving, we are finding it. And why we are writing using approximate and not equal? Because in the real world the data is noisy. We use normal equation or least squares to find the best x. So now it's very clear that linear regression makes use of this equation ax is equals to b. Similarly, neural networks, they make use of a equation y is equals to wx plus b, which is a form of the central equation ax is equals to b. Now let us understand the concept in neural networks. So in neural networks, this is the fundamental layer of almost every AI, from ChatGPT to Tesla's autopilot. So let us understand this equation, the matrix view. So here in neural networks, the small x, the x vector, it is the input. So here x is the input. It's the input vector. Capital W is the weight matrix. And this weight matrix will be holding the weights. And small b is the bias vector. So bias vector, it's an offset. X is the input and W is the weight matrix. So in neural network, we do the matrix vector multiplication operation. So when you run a large model, your GPU is doing matrix vector multiplication billions of times per second. So it is just multiplying the matrix, which is the weight matrix, with the input vector, adding it with the bias vector to get an output. It is comparing that output with the ground reality. The difference is the error, and based on the error, it is updating the weights. It is updating the values in the weight matrix. Once again, multiplying it with the input feature, input vector, adding the bias, and updating, getting the output, calculating the error, and updating the weights. It will keep on doing it until the error is minimized. So neural network also makes use of the equation wx plus b. Even the principal component analysis, it makes use of the matrix operations. So the idea of principal component analysis is like reduce massive data set, for example, of 100 features to essential 3 features without losing information. So that's the concept of principal component analysis. So in principal component analysis, we reduce the massive data sets containing hundreds of features to essential data sets with just 3 features without losing information. Now let us understand the matrix view. Principal component analysis, it calculates the covariance matrix of your data. So whatever data you have, the data set, we calculate the covariance matrix and then find the eigenvectors and eigenvalues of the covariance matrix. Now eigenvector, it points in the direction of the most spread. Eigenvector points in the direction of the most spread, the variance. So in your data, by keeping only the vectors with largest eigenvalues, you effectively compress the reality of the data into its most essential parts. So keeping the largest eigenvalues, you can eliminate other eigenvalues. So you can just compress the reality. You can get rid of unnecessary features, and you can transform hundreds of features into essential 3 or 4 features without losing information. And that is what principal component analysis is all about. So in principal component analysis, we convert our massive data set into a covariance matrix, and we get the eigenvectors and eigenvalues of those covariance matrix, and we make use of those eigenvalues and eigenvectors to reduce the massive data set into fewer data sets, fewer features without losing information. Now, these recommendation systems, it also makes use of the matrix operations. So, recommendation systems, they make use of matrix factorization. So, the concept of recommendation system is very simple. Like the idea is predicting what you want to buy before you know you want it. So, recommendation system will recommend you that you should buy this. Now, the matrix view, let us understand. So, imagine a giant grid where every row is a user and every column is an item. So we have a user item matrix. So in the user item matrix, every row is the user, every column is the item, and the numbers are the preferences. And it is like a sparse matrix. Most of the cells are empty. Now what we do here is we take this giant user item matrix, I'm calling it R, and we are breaking it into two smaller skinny matrices U and V, such that U times V is approximately R. Now, this process of decomposing a user item matrix into two smaller U and V matrix reveals hidden features like user 1 likes action movies and movie X is an action movie, allowing the AI to fill in the empty cells with high accuracy guesses. So we do the matrix factorization. So in recommendation systems, we do the matrix factorization. So we start with a user item matrix and we break it into two small matrices U and V such that U times V is approximately the user item matrix R. And this U and V matrix, they reveal the hidden features which helps the AI to recommend to the users. So now it is very clear to us that machine learning is mostly matrix operations. Regardless of what algorithm you are using, any famous machine learning algorithm you take, you are doing some sort of matrix operations. And now one very interesting discussion we will do. Now this matrix operation has a very interesting hardware connection, especially with the GPU. See, the reason we use matrices in machine learning algorithm is not just because the math is elegant, but because of the efficiency. So the idea is if we use CPU, central processing unit, so CPU is like scalar operations one by one. But with GPUs, graphical processing units, they are designed to process entire rows and columns at once. So we can perform simultaneous or the parallel matrix operations. We can perform billions of operations simultaneously. And there matrix comes into the picture. So if we use matrix, we can efficiently utilize the computing power of GPUs. With GPUs, we can perform billions of operations, matrix operations simultaneously. So the reason for using matrices in machine learning is efficiency. So without linear algebra, AI would be millions of times slower because we know that AI, it is compute intensive. So without linear algebra, the operations would be very slow. AI would be millions of times slower. Linear algebra makes real-time translation, image generation possible. Now let us look at the significance of AX is equals to B. Significance of the equation AX is equals to B. So the equation AX is equals to B is the master equation of modern computing. So while this equation looks a simple algebraic statement, it serves as the universal interface between human logic and machine execution. So this equation AX is equals to B, it serves as the universal interface between the human logic and the machine execution. Now let us understand the significance of this equation in certain critical domains. So in linear systems, this equation is the core of linear systems. So this equation is the most direct application in linear systems. Any problem where you have multiple constraints and multiple variables can be written in the form of Ax is equals to b. Now the significance is this equation allows us to solve for hundreds of variables at once. Because in this equation, this x is not just one variable, but it is a vector. X is a vector, b is a vector, and a is a matrix. So we can solve for hundreds of variables at once using this equation. Like balancing a chemical equation or calculating the load bearing capacity of a bridge. It uses algorithmic methods like Gaussian elimination. So linear systems, they make use of algorithmic methods like Gaussian elimination. The core of linear system is this equation, Ax is equals to b. In neural networks and deep learning, this equation, the master equation, acts the engine, acts like the core engine. Ax is equals to b. So in a neural network, every thought is a matrix vector product. So in neural networks, X is the input, like for image, it can be pixels. A is the weight matrix, the knowledge which it is learning, and B is the bias, the next layer activation. So here B is not the bias, sorry, B is the next layer activation. Like when I multiply the input with the weight matrix, the output I'm getting, that is the B, and B I will send it to the next layer. So B is the next layer activation here in this equation. So Ax is equals to B is the engine of the neural network. X is the input, A is the weight matrix, the knowledge, and B is the next layer activation. Now in deep learning, in a deep network, is a simple chain of Ax is equals to B. So initially we are starting with A1x, the result, we're multiplying it with A2, then A3, and every time this A we are updating. So it's a stacking operation. So linear algebra allows us to stack these operations to create complex artificial intelligence. So with linear algebra, we can create complex AI. Now, this master equation Ax is equals to b, it also has a role to play in optimization. In optimization, this master equation, it provides a direction. Now see, optimization is the process of finding the best version of something. Like optimization is like minimizing the loss, maximizing the profit. And AI optimization is minimizing the loss. So basically, in AI, for optimization, we calculate the Hessian and the Jacobian, which are just the matrices of derivatives as A. So in optimization, the capital A is the matrices of derivatives. So capital A is the Jacobian matrix or the Hessian matrix. Now, it is used to find the direction to move to optimize the parameters. In regression and least squares, the central equation Ax is equals to B, it helps us in giving the best fit. So in the real world, Ax is equals to B usually has no perfect solution because the data is messy and noisy. So no perfect solution we can expect. Rather, we will be going for the best fit. So least squares is a technique to find X, making Ax closest to B. So least square is a method of determining the unknown X. When we multiply it with A, we get not exactly equal to B, but close to B. Similarly, in regression, this is the math behind trend lines. In regression, we are predicting a continuous value, like we are predicting stock prices or housing trends. And in regression, we make use of a normal equation. A transpose into A into X is equals to A transpose B. So what we are doing with the central equation, the master equation Ax is equals to B, both the sides we are multiplying it with the A transpose A transpose. So we are calling it the normal equation, and we make use of it to minimize the distance. So now it's very clear that the master equation Ax is equals to B, it has a role to play in least squares and also in the linear regression. Now the central equation Ax is equals to B, it also plays a role in scientific computing wherein it helps in simulation. So modern science, it runs on simulations. Like we simulate the weather patterns, we do simulations in fluid dynamics, nuclear physics. So simulation problems are usually defined by differential equations. Computers cannot solve differential equations directly. So they have to discretize differential equations into millions of tiny linear pieces. So computers, they discretize differential equations into millions of tiny linear pieces. So basically, we turn a complex physics problem into a massive Ax is equals to B problem. So the tiny linear pieces are Ax is equals to B. So in solving differential equations, we like the computation, the computing, the algorithms, they convert or they discretize the differential equation into millions of tiny linear pieces. Ax is equals to B. So we are turning a complex physical problem into a massive Ax is equals to B problem that supercomputers can crunch. So that's the idea. So in scientific computing also, this master equation Ax is equals to B has a role to play. Now it is very clear to us why Ax is equals to B is the central equation of the linear algebra. Why it is called the master equation of modern computing? Because this equation has a role to play in linear systems, in neural networks, deep learning, optimization, regression, least squares, scientific computing. So in this equation, why this equation is so powerful? The secret is the linearity. Why the central equation is so powerful? The secret is the linearity. The reason Ax is equals to B is the foundation for everything is that non-linear problems are incredibly hard for computers to solve directly. So the strategy is, so the non-linear problem are hard to solve. So what we do is, the strategy, we take a curved, messy, non-linear word and zoom in until it looks flat, linear. So the strategy is to zoom in on curved or messy word until it looks flat, linear. And by treating everything as linear systems, we can use the most optimized code ever written for speed, for efficiency, to solve problems at the speed of light. So the linearity is the key. So the idea is very clear that any non-linear problem is hard. We have to convert it, we have to transform it into a linear problem. And with linear problem, we can make use of the GPU, wherein we can carry out billions of computations simultaneously. So the bottom line is, if you can express a problem as a Ax is equals to B, you have a path to a solution. So the idea is that we just have to convert or express a problem as Ax is equals to B problem. And if we are able to do that, then we have a path to a solution. And if we are not able to do that, then we are stuck in the dark.